All right, it's 10:15. I think we'll get started. That's pretty loud. You guys can hear me really well. Hopefully that's okay. The only problem is going to be I had a cold last week, and I'm still trying to get over this terrible cough that I have. So hopefully when I cough, I don't blow out your eardrums. But we're going to get started. And I hopefully put enough buzzwords in the title to get you guys to come in here. How many people are looking at doing microservices style architectures? Okay, you came to the right talk, I think. This slide deck, so I have only 45 minutes, and I'm going to try to, I'm kind of a bit crazy because I have so many slides and so many things to say on this topic. I'm also going to try to do a demo, and I'm going to try to cram this into 45 minutes. But this talk is actually much, much longer. The full slides are here. If you can go here, the full deck is about 90 or 100 slides. The deck that I'm going to use today is like 50. And there's no way I'm going to be able to do that unless I keep a really good pace, so I might go a little quick. At the end, I'm going to try to leave time for questions, but I do plan to, after this talk, go out back, and then we can have questions afterward. Okay, so let's get going. So first, real quick, my name is Christian. I'm a principal architect at Red Hat. I spend a lot of time working with our customers in North America and helping them understand how to build resilient distributed systems. My background is in integration and messaging. I spent a lot of time at Zappos.com and their parent company, Amazon, and got to see, this was maybe now 5 years ago, what DevOps and microservices, although we didn't call it that back then, but what a mature, high-performing organization looks like, and understand some of those principles and how to guide enterprises that don't look like Amazon, but what that journey might look like for them. I'm also committed on a bunch of open source projects and love talking about this. And I recently wrote a book, I guess it's not recent anymore, it's about a year ago, Microservices for Java Developers, where if you go to developers.redhat.com, you can get a free electronic copy. And downstairs at the booth, I think they have hard copies. So there you go. Now, everyone's talking about microservices, and we've been talking about that for the last 3 years now. And I think we've come to this point where we've talked about it so much that everyone just thinks, well, if we just follow these things, if we just check the box on all these things, break things up smaller or whatever, add single database per microservice or whatever, then we'll be doing microservices. But the reality is, it's more of an evolution or a journey that teams and the organization, with its structure and its culture and so on, that they take to be able to go faster. That's the ultimate goal, not doing microservices or SOA or whatever, any of these technology. We as developers especially, how many developers in the room? Yeah. As developers, I get at least, distracted by all of the really cool technology that's coming out, but it's definitely going to be, this journey is going to be an organization-specific journey. Netflix did it their way, which is different than how Amazon did it and different how Google did it. Just like any of our enterprise companies are going to have different challenges going down this path. But like I said, I have a cough coming. Like I said, microservices is about optimizing for speed. How do we go faster? How do we do faster deployments? How do we get feedback loops and understand whether or not what we delivered into production is what we think it is and is worthwhile? We want to reduce the amount of time that we have between starting a project and delivering it and getting whatever value that we can out of it. So we want to optimize for speed. But how does your company go fast? How does any company go fast? There's layers and layers and layers of complications there, but I think putting all those aside, because those are different talks, talking about managing dependencies between the different components in your system and even reducing those dependencies where you can is that key. It's also easy to say, but that is the key to being able to be more autonomous and make decisions independently and go faster. And I think data is one of these major dependencies. How systems share data, how they interpret data. These, there's all kinds of intricate implicit dependencies between the teams and systems that if it's implicit, then you're not as motivated to go and solve for some of these things, or you don't see it and it's not very clear. But before we start talking about some of these issues, I want to define what is data anyway. What are we talking about when we say data? And I think what has helped me understand it a little bit better is describing it as because when we talk conversationally between humans, we can have a conversation about certain concepts and on the fly disambiguate some of these things, right? But the data that I'm talking about is a conversation with another human, but through the computer. We're going to try to explain these concepts to the computer first. And then, hopefully, we're going to read it back, and some other human might be able to interpret it. That's the goal. We're trying to explain these through conversations through the computer. But the computer doesn't have this extra context that it might need for you to intelligently understand what the purpose of that data are. So I can illustrate that real quick with a description of how even if you go through this exercise and you just try to describe what a thing is, what are one of these concepts that we want to describe, that we want to tell the computer so other people can go back and see. I use the concept of a book. Maybe we're a library or a e-retail or something, but we want to model what is this idea of a book. Now, how do you describe what one book is? It's got title, cover, pages, I don't know. But you can very quickly get into a situation where you describe a book as one thing, and then you say, well, in my example, I've only written one book. But there's multiple copies, so I could have multiple copies of the book. How do we describe that in the system? Other people have written multiple books. Each one of those is a book too, and so are all the copies. But sometimes people write books that are so big that they're broken out into smaller volumes. Now, is each volume a book? Or is the whole thing a book? Or a newspaper has a cover and words and so on. Is that a book? Where do we draw that line and how do we describe that? Really depends on who's asking the question. What is the context associated with the question? And in this case, we could easily say that a book could be described in different parts of our system differently. So a book checkout and ordering system might want to know about every single copy of the book. And there's probably more metadata associated with that than let's say, the title search engine, where we just really care about titles. Or maybe the recommendation engine, where we don't really care about titles per se or authors per se, but maybe we care about abstract metadata, like how different categories or different topics relate to each other, and so on. So we have these different boundaries that start to naturally arise depending on who's talking about these concepts, even though these are shared concepts and potentially shared across all of the systems. And I think that's where practices like domain-driven design come into the picture, because although I just used a very simple example of a book, our domains in our enterprise companies are far more complex, far more ambiguous, sometimes even conflicting, and domain-driven design and the patterns and practices around that have come up to help solve complexity in the domain, which is where we start to find these data problems. Now, you're probably thinking, well, Netflix doesn't talk about domain-driven design. LinkedIn doesn't. These internet companies don't talk about domain-driven design per se. and to me, the answer is pretty simple. Going on Twitter and posting a tweet on Twitter is far more is simple. You just go on there and you post or update your LinkedIn profile or whatever. That's simple stuff. Our businesses, our enterprises, and our financial services companies, and our healthcare systems companies, and our insurance companies, and retail, and so on, these are far more complex. They've probably been around for a lot longer, and it's not as easy as what some of the internet startups had to deal with. Now, the internet startups had to deal with data problems at scale. So I go and do a tweet on Twitter, but now I have to show that to potentially 500 million people. And sorting and linking and organizing, that gets really hard. But I think our enterprise companies are going to face challenges at that kind of scale too, but we should not overlook the complexity inherently in the domain, and we should solve for that as well. So anyway, we get going. Now let's say we do domain-driven design, concepts like bounded context and context map and aggregates and all these patterns that have come up to help solve some of these challenges. And we build out our modular system and so on. And then we put everything into a database. And over time, as we make changes to the system, these boundaries start to erode, and the database schema, maybe that erodes. But the inclination, at least starting in 2005, when we started going to NoSQL and all these new data stores, was to just, we'll just throw away the relational database. And I'm absolutely confident that the way we were doing things in SQL and the relational databases was really powerful, really, really, dare I say, even awesome. I don't know if I should say that, but SQL and the things that it does for you, normalizing your data structures, allows you to do very powerful things like queries. Queries against data and even ad hoc queries are queries that you didn't even think about when you started writing this data. Being able to do complex joins and relationships that weren't originally thought of ahead of time. That's pretty powerful stuff. In the alternative world, in the NoSQL world, you have to think very, very hard about what your queries are going to be ahead of time and hope that that stays true for the life of your application. But so SQL normalization is actually really good stuff. The second thing, what we're terming ACID, having this abstraction of transactional behavior. So just looking at atomicity for a second. If the database and the underlying frameworks underneath can abstract away really hard problems like partial failure and partial implementations of transactions, that kind of stuff, if it can solve for that, that's powerful. Developers now don't have to worry about that in their code. Things like isolation. When you have multiple applications or multiple threads in your application trying to talk to the database, and the database just says, don't worry about concurrency, don't worry as much about concurrency. We're going to make everything look like it happened in one nice little line. That's pretty powerful. Durability, making sure that we don't lose stuff. The C, anybody know what the C in ACID stands for? Right, but it's not the same consistency in the CAP theorem. So there's a lot of angst about what that C really, what does the database really do for you in that scenario? And we'll come back to the CAP theorem in a second. But all of these things really make the developer's life a lot easier and even comfortable in some ways. So the C, for me, stands for comfortability. Stick with these conveniences as long as you can. These are powerful abstractions. But as you start to grow and as you start to hit some of the limits, the inherent limits around these, and these are inherent limits, in my mind, the context is the traditional relational SQL database. There's some new technology like the new SQL stuff that might solve around some of this stuff, but we're not going to talk about that right now. But we will evolve and we will grow, and we want and architect our application so that they can change faster, and so we introduce this isolation and autonomy. But what we're really saying here is when we start to move away from this model is that, thank you, database. You've been awesome the last 40 years or whatever it's been. You're pretty much bulletproof, but we got it from here. We're going to do it now. We're going to do this stuff. And then we come up with things like, well, a microservice and microservice architecture. Microservices should have their own database. Now, now we start going down the path of some of the problems that we have to solve for in this model. Because we think if we just isolate things and isolate the data and the service owns the schema and all that stuff, we can change it a lot faster, which there is some merit to that. But we're also now building a full-fledged data-driven distributed system. And distributed systems are not easy. They're not trivial. Even though we might think, well, what's the big deal? Where A is calling B, and B might call C, and we might have some over-the-network calls. But that word, the network, is a big problem. And unless we take the network seriously, we're going to have some bad experiences. So when I say the network, I mean, so this looks nice and simple, but what it really looks like is something like this. And in this network, these are asynchronous networks, and that is key to understand. These are inherently asynchronous. And what I mean by asynchronous is things talking to each other on the network don't share the same concept of time. These are asynchronous in terms of time. When I send a message, it's not going to get there immediately. I have at least, to go over a wire on fiber or whatever, I have at least the speed of light delay, right? So there's going to be a delay. Next, I have commodity hardware. Things can fail. Next, the way our IP networks work is based on packet routing and queuing. So we can have arbitrary delays randomly for no explanation. And these delays can look like failures, and failures can look like failures, and you can't really detect which is which. So this underlying premise drives, I think, the rest of, if we're going to start building these data-driven systems, we have to take this part into account very seriously. And I think the follow-on from that is that go check out this paper. It was written in 2005. And so none of the stuff that I'm saying is actually new. Hopefully I can try to put it together in a nice way. But none of this stuff is new. We've been talking about distributed systems for a long time. But the data inside our services should be treated differently than the data outside our services. Pat Heelan wrote this paper. I think he was at Microsoft at the time. But the point is, when services communicate with each other, and data leaves the service, a service, whether that's through, maybe I published a message on a message queue, or maybe I queried a service and got some data back. As soon as the data leaves that service, excuse me, we have this very distinct notion of the data was back then. It was current back then, not right now. This is old, right? If we have time delays when we're talking to our services, by the time I get the data, it could have changed. So there's some inherent staleness built into the system. But if we're talking about the data inside a service, inside, let's say, one of our bounded contexts or one of our ubiquitous languages in the domain-driven design parlance, if we're talking about the data inside those services, those can be and should be now. We know we have a certain level of consistency, and we'll come to that, and we know the data is now. So we have then and now. We have this inherent staleness. But so when we start looking at how do we build applications on top of this foundational architecture of the network and this premise about then and now, we need to build these things into our system as first-class citizens, I think. Because some of the application level problems that we start to experience because of this, sharing data across these boundaries, I'll try to illustrate now through a couple examples that, I do run into these examples. They're not totally contrived, but some of them are to make a point. But when we start doing something in our application, our service, like maybe we want to update an address. Updating an address sounds simple. We'll just go to the database and make a change and update the address. But address might be a concept implemented and designed in its own context in other parts of the system, other boundaries, other bounded contexts. So, for example, the shipping service, so maybe this is the customer profile service or something, but the shipping service will want to know when a customer updates their address. Because what if there's stuff in flight that needs to be rerouted? Or the recommendation engine, or the advert engine that displays certain ads depending on where you are. Or the tax calculation service. Depending on where you are, you're going to calculate taxes differently. These systems want to know when your address changes. So we need to somehow tell them. But if we naively just publish, just naively publish this information without taking into account, well, what are the consistency guarantees am I going to get when I do this? We end up with, I mean, I'm hoping a lot of you will recognize that what happens if we commit and then we fail and we don't even publish downstream, right? Then we get into an inconsistent state. Or what if we publish first and then fail and we don't commit? And we have these inconsistencies. So we can do things like maybe coordination across boundaries, and that, you know, I think we've historically tried to look at the problem through that lens. But this introduces its own set of challenges. Doing two-phase commit, I think, is perfectly fine in your own boundary, where I showed that premise where inside a single service we have now, but outside of a service we have then. So we shouldn't try to do two-phase commit XA transactions across our boundaries. That gets really hairy, and come ask me later. I can go into more detail. But then we do things like, well, we'll just call all these services individually, and we'll do the dual write, triple write, whatever. And then we end up with, well, if some of these calls fail, we'll just try to do compensating transactions. And then you end up having to store that state and the transition of that state and the compensating actions, because what if you fail? Because then you need to come back and be able to properly execute the compensation. Kind of sounds like a transaction manager. But even more, what if the systems weren't actually built for this kind of thing? Because what we're doing here is we're saying, let me update you with let's say the customer profile got updated, address changed or whatever. Let me update you with the address. Oh, I couldn't call this one. Now I need to roll back, change my mind. What we're really saying is, if you look at this through the lens of a traditional database, we're saying we can get read uncommitted. We can get the lowest level of isolation in the database, which is, we never do that. We can get into a situation where this address change happened and was visible, and people made decisions based on this, and then we say, oh, changed my mind, roll it back. And that might be okay, but that is an often unknown or overlooked problem that you can encounter here. Now, another one that I see is, okay, cross your fingers for me. The next problem that I see is this, where we can do queries against a service, and we may potentially return an unbounded list. So maybe we query for certain types of customers, and that list can be crazy huge. We don't really know. But the thing is, when we get that list, we want to iterate through it and enrich. Is this working? Can you hear me? All right. And enrich that data somehow. So we might make calls out. For each element in that list, we might make calls out to downstream service to do some sort of enrichment. Now, and this might be okay if your downstream service can handle 10,000 transactions per second forever. But that's typically not a good design pattern. But what we end up with is we end up trying to design different bulk APIs, bulk interfaces. For, well, maybe we'll just do, I don't know, we'll just get a giant chunk of hats or whatever for all the cats or whatever. But then we started going down this path. Well, we actually need to filter out some of these. So we don't really want all of this stuff. We just want, I don't know, some hats for cats except these cats. But then we might even just say, well, really, we just really care about certain types of hats for these certain types of cats. And we get really fine-grained. And every API and every service is going to implement this totally differently, and pagination totally differently, and it gets a big mess. And then ultimately you end up with, well, just, damn it, just run this SQL for me. And we're trying to not do that. Another problem, you might solve this through, well, we'll just do caching. We'll just pre-cache, or we'll cache some of the hats for these cats, and now you have to deal with data invalidation problems. So what we really are trying to do across these services through updates and reads and so on is achieve some type of consistency, but we started off by saying that we're going to have to deal with failures as a first-class problem in our architecture. But this sort of sounds like distributed systems theories and CAP theorem. Who's heard of the CAP theorem? A couple people. So the CAP theorem basically says, I'm going to be very, very terse with it, but basically says you have C, consistency, which is different than consistency in acid. You have A, availability, and you have P, partition tolerance. And what that means is, or what the theorem says is that out of those three, you can pick only two. You can only pick consistency and availability, or partition tolerance and availability, or partition tolerance and consistency. But really, you can't pick, or opt to not pick P. P, partition tolerance, is when the networks start behaving asynchronously like we described earlier. If things start to look like they fail, or they do fail, or they partition, or whatever. But you can't trade off P, you get P. You have to pick C or A, so the CAP theorem says. You need to pick, I want strict consistency or I want availability. Now the problem with the CAP theorem is it describes consistency and availability in the most strict definition of those words. Consistency, for example, CAP theorem says is, the CAP theorem talks about linearizability, the most strict version of consistency. But consistency models are not just the most strict. There's lots and lots of different consistency models. And if you go into the longer version of the slides, I'll explain a little bit more what consistency models are and what each one of these is. But CAP theorem talks about this. And for availability, it talks about the most strict definition of availability. But there's shades of gray. And if you look at, for example, sequential consistency, strict consistency basically says if I make an update, that update is visible to everyone in my cluster immediately. There's no delays. Sequential consistency says we'll have this nice ordering, but you might not see those changes right away. There might be a delay, but you see everything in order. Causal consistency, you probably won't see everything in a total order, but the things that should be related, like, so for example, updating or commenting on a blog post, I want to see that the blog post was created and that if there were comments, that came afterward. I don't want to see that in the reverse order. So there was a causal relationship between those events, but just those events, and I want to see those in that order. But across all of the blog posts, I don't really care. And on and on and on until you get down to eventual consistency, which really just means I can read anything. Whatever. And funnily enough, if any of you went to the baseball game, Doug Terry, who I think is at Amazon now, he wrote a paper describing these different consistency models through abstract concepts that are made more concrete in baseball, the game of baseball. If you're the umpire, you might need a strict consistency, or you probably do, but you also might be able to get away with something like read my rights. So as an umpire, as a scorekeeper, if I'm a scorekeeper, I just need to know what is the last right I made so that I can increment the scores, but everybody else, they might see the score differently. So for example, if you're getting radio updates, I want to see a version of consistency that increases over time. I don't want to see things go backwards. So I might just need monotonic reads consistency. Or if I'm a sports writer and I'm writing my article tomorrow or the next day or whatever, then eventual consistency might be perfectly fine. So there's different classes of consistency, but maybe we can take advantage of some of these shades as we start to build out these systems. And here's an example of maybe updating the customer profile using in this case, we'll use a sequentially consistent cube, where we make our updates, and we record those in this queue, and it's sequentially consistent. So we'll see everything in order, but a little bit later than it actually happened. But as soon as data leaves the service, it's a little bit later anyway. So why don't we just make that explicit? And then the systems downstream, they'll see all of these events in the right order, and then they can process those and update their local store, their local databases, the way that they want to store things, right? So now when we get to this thing where we talk about microservices have their own databases, and they want to take advantage of maybe their own schemas, maybe there's different I/O properties. They can deal with these data changes across boundaries at their own time in their own way that they want to on their own databases. So, but what we've done is gone off and we built this if you think about what I just described here, in terms of a relational database or your regular database, regular databases have this concept too. They have things called views. They have things called materialized views. And the database is responsible for keeping all that stuff up to date for you, and it works really nicely when you use it. But when we start to distribute this out, now we're building materialized views. Now we're building a database across our applications. Now, for these types of problems, there's interim steps, right? This is not just a go from what you have today to just go to event-driven systems tomorrow. I think there are interim steps. But this isn't some totally crazy idea either. This is what the internet companies did to build their data systems at scale. And some of them even open sourced some of their technology for doing this. Now, building a system with more relaxed consistency in more of a stream-based model was done at, for example, Yelp. Yelp built all this stuff around MySQL, so the relational databases were able to turn the relational database into a set of streams, and downstream systems could react to the changes coming from that stream. But the problem is they also built up a lot of other stuff around it that if you're going to use this, you kind of have to use all of the stuff. And you have to buy into, well, just using MySQL, because that's what they built around it. And operationally, there's a bunch of other stuff. But so and LinkedIn did something similar. They have, I think it's MySQL and Postgres. And then Zendesk did something similar. But what I was really interested in seeing, can we do this in open source communities? Can we do this in a more open source way? And even though they did throw the code over the wall, open source, but can we build a community around this and make it much more modular instead of, here, if you want to use this, use everything. And I think that's what we did with Debezium.io. So Debezium.io is a very simple system that allows us to take advantage of building out different levels of consistency across our boundaries, across our services, and properly deal with the problem of having multiple databases per service, or a database per service. So what Debezium is a change data capture system. It's not new. CDC has been around for a long time. But it's an open source change data capture system that allows you to take the changes that happen in your database and take those changes and turn them into a sequentially consistent queue, a stream. Excuse me. And do this in a modular way so that we can support lots of different ways of running this. So we can run this against multiple different types of databases. We can run it in a way that sort of the default canonical way of using Debezium today is using, I guess I'll talk about that in the next slide. But you'd be using some specific technology. But what if we wanted to, what if we didn't want to use that specific technology? What if we wanted to do it a different way, our own way? But so what Debezium is a set of database connectors that we can use. We can point those at a database, and what it does is read the database's transaction log. So the database is already doing this. That is how the database implements its own replication. It keeps logs, change event logs, and that's how it comes up with the current state of the database, and that's how you do replication. But Debezium basically acts as a slave or a follower and reads the database's transaction logs, turns that into a concrete stream of events that it then publishes out to some sort of queue. And we have support for MySQL today. That's been there for quite a while now. We have recent support for Postgres. We have MongoDB, and I think Oracle and maybe the Microsoft one are next on our plate. So specifically the technology that the canonical way of doing it is we've created these modular connectors. So this is maybe a MySQL connector. And we can take that connector and we can deploy it in our Java apps. This is a Java-based system. or anything, really, if we want to just take the connector. But if you want to create a data pipeline system, the canonical way of deploying it is just into a framework called Kafka Connect. Has anybody heard? How many people have heard of Kafka? Okay. How many people have heard of Kafka Connect? Cool. So Kafka Connect is a framework for building data systems that allow you to ingest data from databases or files or whatever, from source of data into Kafka, and do it in a highly available, reliable way, and also take data out. So there's connectors for consuming Kafka and putting them into like a Hadoop or whatever, like just some sync application. But Debezium uses Kafka Connect as a source where we can point Debezium at these databases, and now the framework just takes care of sucking down the transactions logs, parsing them, and taking each record and putting them into Kafka. So each table ends up turning into a Kafka stream. Everyone with me so far? So now we can look at maybe to pick one of those examples that we saw, but this helps in a lot of those examples, where you end up with, maybe we just want to pre-cache or cache a lot of those hats for cats, and we can just use Debezium as a streaming data platform to, whenever changes happen in that database, invalidate the cache or update the cache. So we have we know it's cache, we know things are stale, these are sequentially consistent, we'll get everything in the right order, but then Debezium handles those updates for us. And actually we have I'm not a product manager, so I can't say how this will end up being productized or if it will, but we do have a data federation product today that can help with some of the interim steps of getting to a full-fledged event-driven system, but that I think will use Debezium as part of its implementation for building these types of materialized views of services. So what we're saying is, use domain-driven design, get boundaries around your services, focus on the transactionality and the now of those services. Those services will then communicate by sending events between each other across these boundaries in a sequentially consistent or other consistency model between each other. And then in a full-fledged microservice environment, what you then end up with is a set of services that end up being your transactional services, but then the data from those services ends up being published in some way as events onto this stream that then you can materialize however you want. Now the queries, instead of doing so, Netflix talks about their API gateway and their API implementation and all that stuff. And what they're basically doing is calling all of these backend services and doing lots and lots of joins in application code. I think doing it this way, where all these joins are pre-computed and constantly being updated, so that the queries to these views now are much simpler. They're flat select statements. Is in some use cases is much more advantageous. So you end up with services, sort of data services, and you end up with your transactional services, and they're combined through this event-based architecture, event-driven architecture. And I do have demos of that whole thing. But I also want to point out that Debezium isn't just some scientific project, that there are companies out there using it, some of them public, some of them not public. Even though it's an open source project. This is an open source project. It's not a Red Hat product yet. But WePay.com uses Debezium for exactly this purpose. And they've written about, I guess go to the slides, but they wrote a blog on it. They went into great detail about how they use Debezium with MySQL to build this, their microservice architecture and solve some of these data problems. So I got 5 minutes. Let me try to do the demo, and then if there's time for questions, or we can have questions outside. I'm sorry, I just so much stuff to talk about. But let me see if I can get into a demo here. Can you guys see this okay in the back? Maybe I can try to make it a little bit bigger. But so I'm going to show Debezium, but to show Debezium, I'm going to show Kafka, because Kafka was part of this. I'm using Kafka as a queue. To use Kafka, I have to use Zookeeper. So we're going to start up some of these pieces. So Zookeeper came up. Now we're going to run Kafka. We're running this all in Docker, so hopefully it should just work. So Kafka came up. We're going to create a MySQL database. Cross your fingers. This is where things like to go sideways. Go, go, go. All right, cool. Now we're going to create a client to the database using the MySQL command line. It's kind of at the bottom. And we're going to use so the Docker image had a pre-populated database in there. We're going to use the inventory database, and we're going to show the tables. We just have 4 tables in here, just dummy data to illustrate the point here. Let's select everything from the customers table, and we'll see what records that we have in this table. Now we're going to start up Kafka Connect and Debezium. So Kafka's running. We're going to start Kafka Connect, and we're going to point Debezium at this database that we just started. And we can see that there is some data in the database. So let's start up Kafka Connect. We don't have any connectors, or we shouldn't have any connectors. We don't have any Debezium connectors. We're going to create one right now. Let's look at what a connector definition might look like. It's JSON. We're pointing it to what the database is. We're telling it to use a MySQL connector, if you can see that at the top, hostname, password, port, and all that stuff. We can do whitelist, blacklist of what databases, tables, and we can filter based on that. So we're going to tell Kafka Connect, create this MySQL Debezium connector. 2 minutes. And we can see that it's doing something. What it's doing is it's connecting to MySQL, it's reading the transaction logs, and it's parsing them and putting each change event, each TML into Kafka as an event. Now, we should see that our connector's there. Cool. All right, well, we can do this too. Running out of time. So I just queried to get the connector config back. We can see that it's there. Everything looks fine. Now we're going to shut off Kafka, or we're going to leave Kafka Connect. We're going to keep it running, but we're going to navigate away from its logs. If I scroll up, you can see that it's still running. And then we're going to log into Kafka, and we're going to list the topics that we have in Kafka. We can see for each one of those tables, we have a Kafka topic. We see the customers, the orders, the products on hand. If I query or subscribe to the Kafka topic, we can see we have this gigantic blob of lots and lots of JSON. So these events that have been taken from the transaction log have been put into Kafka as JSON. Now the JSON, if we come here, and if you can see, the JSON for this is basically what is the schema of our data and what's the payload of the data. That's what's in these messages, and that's why the JSON. And furthermore, it's the before schema and the after schema, and the before value and the after value. So we see the full change event. If you want to do deltas, you do it yourself, but you can see what the change event was, and you can more importantly see what the schema is, because we need to somehow support schema evolution in this too. So I think I'm out of time. But if I start making changes, so we do a select, we'll change Anne's name from Anne to Anne Marie. So if I update this in the database, if you watch, it's going to be very quick. This JSON's going to scroll because we're going to see this update happen. It did change. If you look, where's my clicker? The name now, first name here is the before record. It was Anne. And then the after record where it's been changed to Anne Marie. And the schema has also been logged in there as well. So we can do that. Again, look in the database, and we see that, yep, it was changed. Yep, our downstream systems now have this in Kafka. Kafka is replicated and partitioned and all this stuff. If we do a delete, we see something similar where the before, we see a before, is there an after or before? I can't really see that very well up here. But so we would see a before that has a value, and then we see an after that is null. That indicates a delete. And even more, furthermore, we send in this message that for this payload ID, 1004, which we deleted, we're going to also mark it as deleted so that Kafka has this feature called log compaction. So Kafka is actually just a sliding window of events, right? So 7 days, 30 days, whatever. But at the end of those days, all that stuff will be dropped if it doesn't fit in that window. But Kafka can also do log compaction, which says keep all of the keys, for all of the unique keys, keep all of the keys, the more recent versions of those. So you have the entire data set. You don't want to start losing data. But when we do deletes, we can tell Kafka, when you do your log compaction, this record has been deleted. So this is sort of a tombstone message to Kafka that says, when you see this, any keys with 1004, just get rid of those too, because those have been deleted from the data set. And there's a lot more stuff that I won't be able to get to, but I'm already 2 minutes over. Thank you guys so much for coming. Hopefully you enjoy the rest of the summit.